Hey y'all, and welcome to the next lecture in the Practical Packet Analysis online course. We've already learned a bit about what constitutes a packet and how they're built and a little bit of networking basics. This lecture is going to build on that knowledge and is designed to help you learn how to navigate packets and dissect them based on the information found at each layer. Now to do that, we're going to start by explaining why it's important to navigate packets and why you should do that. Obviously, we have this concept of a packet analyzer, so something like Wireshark or TCP dump that is going to do some level of analysis for us. But we're going to take a more fundamental approach and look at the binary and hexadecimal representations of packets and learn basically how to dissect those somewhat visually. Right, and you may think maybe that's not important since I have these tools, but there is something to be said for understanding the fundamental aspects of how packet analyzers work so that you can also perform these actions yourself, especially in cases perhaps when you run into protocols or things that are not necessarily understood by packet sniffing and analysis applications. And trust me, you will run into that at some point, especially if you're focused in the security realm where maybe you're going to run into custom malware protocols and command and control and things of that nature. So we'll do all those things. We'll talk about binary and hexadecimal, converting between them. I'll go through some examples of reading packets visually and breaking those down manually. And we'll do that with what we call a packet map, which is a visual representation of the various fields in a packet and how you can break it down. So this module is particularly important from a fundamental perspective, and I will say it does get a little bit in the weeds. So if you watch through this the first time and you're completely lost, that's okay. That happens to a lot of folks. You may have to watch a couple parts of this a few different times and work through several of the examples I've provided to kind of get this figured out. You'll be learning this probably not too differently than you would learn maybe a math concept, where you really have to work through a few of these yourself to really get it. So watch this and don't fully expect to grasp everything the very first time if you've never done this before, but use this as a reference as you work through some of the example exercises I'll provide. And I think with this video and the exercises between those two, you should be able to get this down pat, and I certainly recommend that. Now, this is definitely knowledge that I don't think everyone will use all the time, but it is, again, a fundamental foundational part of packet analysis, and I do think it's very important going forward. So please do make sure you take some time to at least get a grasp of what's going on here as we discuss how to navigate individual packets, do some conversions between binary and hex, read packets visually, and use packet maps to understand what's going on with our packets when they're represented in hexadecimal format. Now, to begin, most of us know that computers operate based upon electricity and the presence of an electrical signal or the absence of one. And this is often represented in what we call a binary numbering system or a base 2 system. And that's to say we have two digits to work with, a 1 or a 0, with a 1 representing the presence of an electrical signal and a 0 representing the absence of one. So this is how computers generate and store and communicate information. And that's really no different on the packet level. When a system is transmitting packet data across a physical or a wireless medium, they're actually transmitting ones and zeros, which are processed by the receiving system. And then we're abstracting from that binary representation to more human-readable data in a lot of ways. But for the most part, the problem here is that packet data isn't very easy to read as humans in this ones and zeros in this binary format. It works really well for machines, not so well for humans. For example, here's a packet on the screen here. This is a normal packet, so we have an IP header here. We have, I believe, a TCP header here. So this is a normal packet, but displayed in binary format. And certainly, this is not the easiest to read. It would take quite a bit of time to actually dissect this and realize what's going on and do the math to get this converted into something more readable. So great for computers, not so great for humans. So for that reason, we generally don't parse packet data in binary format for the most part. There are some exceptions when we're zeroing in on individual bits as opposed to bytes, but for the most part, we don't interpret packets in binary format as humans. Now, the format we do use is called hexadecimal, and it's a base 16 numbering system. So we have 16 characters. So if you think of the normal numbering system we use, which is base 10, we're talking about the 0 through 9. With hexadecimal, it's base 16. So the other characters in this case, the other 6 characters are actually letters. So we go 0 through 9 and then A through F. So it would be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F. F representing would translate to 16 in the normal base 10 numbering system we count with. So numbering system's a little bit of an interesting thing to think about conceptually if you've never considered anything other than the normal base 10 system. But I think by the end of this lecture, you'll kind of get a sense of what we're talking about. Now, packets are written in hexadecimal format because it's a lot more concise. It's a lot easier to interpret more quickly. So I just showed you an example of a packet in binary format, and there was a lot there. It was a lot to go through. So here's the same packet in hexadecimal format. And again, if you've never examined hex data, this may not mean a lot to you right now, but you can definitely see already this is a lot less data to parse through. It's a lot less in terms of number of characters by quite a large degree. So we've shrunk things down quite a bit. So we're going to talk about converting between binary and hex because that's an important conversion to know. And then we'll talk about, really for the rest of this course, how to use packet maps to look at what you see on the screen here and make a determination about exactly what's going on relatively quickly, at least when you get good at it. So when you do get good at this, you can look at what you see on the screen here and kind of make some determinations of what's going on. For instance, I can look at this and based upon seeing the packet starting with 4.5, I know this is an IP header that starts this packet, a normal size 20-byte IP header. And I can look over where it says 8006 and see the 06 and know that a TCP header is included here as well. So as you get good at this, you'll be able to immediately notice some of those things and notice a little bit about the makeup of a packet just by glancing at the hex data. That's not really possible with binary data, looking at packets that way, but it certainly is with hex, and we're going to explain that in this module. Before we go into how to convert between hex and binary and decimal, we really need to discuss the concepts of bits, nibbles, and bytes as it pertains to the different ways we can view information. After all, packet analysis is really all about viewing information in different ways in order to make decisions about what's going on and come to conclusions about what's happening. Now, in binary numbering, again, we have ones and zeros, 1 representing the presence of an electrical signal, 0 representing the absence of one. And there's a couple different ways to group these things together. At the most fundamental level, we have one position. And I want you to think of things in terms of positions or number of characters or number of digits. In this case, we're talking about one character, so one position, and that represents a binary bit that can only be a 1 or a 0. It's just one singular entity, one recording of whether an electrical signal is present or absent. Now, we can also group this in terms of 4 bits, and 4 bits is what we call a nibble. In this case, we have 4 positions here. In this case, 2 of those, the first one and the last one, are on, and the 2 middle ones are off. So 1, 0, 0, 1 is our binary nibble. Now, a term you may be more familiar with than nibble is the term of a byte. A byte is 8 positions or 8 binary values. In this case, our byte is 100111010. That's our binary byte. So we have 3 different ways we can represent groups of binary numbers: bits, nibbles, and bytes. Now, in binary, that's how we represent these things, but they can also be represented differently in other numbering systems. For example, we talked about hexadecimal. For hexadecimal, a byte looks like this. Instead of 100111010, we have 9A, which is a hex representation of a byte, and it's obviously a much shorter one and maybe even a much easier one to visually parse as humans. We can even take that a step further in terms of abstraction and convert this byte into decimal. And when I talk decimal, again, I'm talking about the base 10 numbering system that we're all used to counting with, going from 0 to 9 and then combining those on to 10, 11, 12, so on. So in a base 10 numbering system, the same binary byte is represented as 162 in decimal. So these are all different ways of representing kind of the same information. And that's going to be important if we want to understand how packet data is represented, and particularly how we get from hexadecimal representations of packets, which are easier for humans to understand, to things like decimal bytes, which are numbers that we're all familiar with. So when we talk about things like ports, for instance, and you're looking at the hexadecimal representation of a port, you may want to convert that to the more familiar decimal port number. So what does port 443 look like in hex, or what does port 80 look like in hex? These are things we're going to answer through the conversion processes we're talking about. The first conversion I want to start with is converting binary numbers to decimal numbers. Not necessarily because I think that's the thing you'll do the most often, but it is really the most fundamental way to look at going from a binary number that you don't quite fully grasp to a decimal number, which you should grasp because that's the numbering system we're used to in counting on a daily basis, that base 10 numbering system. So to do that, we're going to start with the byte I have on the screen here. And so this is a byte consisting of 8 binary bits. Some of those are ones, indicating presence of an electrical signal, and some are zeros, representing absence of one. And I want you to think about these numbers in terms of positions. And I stress the importance of positions because each position has an inherent value associated with it. And those values are on the screen here. You see on the right-hand side, we start with a value of 1. We double it to 2, double it to 4, double it to 8, and so on all the way up until you get to 128. So each position has a value. And any place where a 1 exists in that value is a place where we take that value and then we add them all up. Right, so in this case, starting from the left, you see that the 128 position has a 0 in it, which means we don't take that value. We ignore it, we discard it. However, if we go to the 64 position, it does have a 1 there. So we do take that value. So we can look across this byte here and see that we have 1s in the 64 position, the 4 position, the 2 position, and the 1 position. So we take all those values, and all we really do is just add them together. So 64 plus 4 plus 2 plus 1, and that equals 71. And that is a decimal value that represents the binary byte we have on the screen here. Pretty straightforward, right? That's not too complicated as long as you can remember what the values are that each position maps to. And that's easy enough. Remember, you just start with 1 and double it all the way to 128. So let's do that again. Let's do one more example. In this case, we're going to start with this byte, and the value is 10110010. So let's look at all the places where we have a 1. We have a 1 in the 128 position, the 32 position, the 16 position, and the 2 position, right? So that's it. So just those 4 positions. So it's the same number of positions as the last example we looked at, but they're actually in higher valued places, right? So we already know the number is going to be larger. So if we take 128, add 32 plus 16 plus 2, and we get 178. So this byte, 10110010, is equivalent to 178 when expressed in decimal. Again, remember, these are just different ways to look at the same information, and this is a way that we as humans can understand this information better than the binary data, which is a lot more understandable and easy to process to machines. So the process we went through here, pretty straightforward. You calculate the value of each position. So in this case, we know that each position with a binary byte has a specific value associated with it, and the places where 1s are present are the values we accept. And then you simply add those values. And that's how you get from a binary number to a decimal number, and that's really one of the simpler conversions we'll do. So let's take the knowledge we just learned with converting to binary to decimal and apply that to doing a binary to hex conversion, which is going to be very similar, but just going to have a little bit of a tweak to it. So to start out, we're going to use the byte 01000101. Now what we're going to do, now if you remember looking at the example I showed earlier where I compared a binary byte to a hex byte, the binary byte was 8 bits, so it's 8 positions we see here, whereas the hex byte was 2 positions. Now to get to those 2 positions, we're going to take the binary byte and divide it in half. So that's what we're doing here. We're actually dividing that into 2 nibbles. And if you remember the values of the positions I talked about earlier, the lower valued positions are on the right and the higher valued positions are on the left. We call those the lower and higher order portions of the byte. So when we refer to nibbles, we can refer to them in that way. On the right-hand side, we have the lower order nibble. And on the left-hand side, we have the higher order nibble. And that's just a way you can reference each specific nibble when you divide those out from a byte and you want to reference those specifically. Instead of just saying the leftmost or the rightmost nibble, you can say higher order or lower order. Now, in this case, each of these positions has a value as well, but the values change because we're treating these two nibbles as separate entities. So instead of going 1, 2, 4, 8, 16, we're actually just going 1, 2, 4, 8 for each one independently, right? So each position, again, we're treating these as two separate entities, not the same whole entity. In that case, we only get up to 8 instead of going all the way up to 128. So hopefully that makes sense as we're treating these separately. But once we've treated them separately, the same concept applies. We're still looking at each position, and any place a 1 exists is a place where we accept that value. So let's look at the higher order nibble first. In this case, we have 0, 1, 0, 0, and we only have a 1 in a single position. We have it in the 4 position. So there's nothing to add here. We just accept the 4, and that's what we have. So we start with 4, and that 4 is the hexadecimal representation of our of what we have here on the left. We're converting to hex and not decimal here. In this case, 4 and hex and decimal are both the same number, so that might be a little tricky. But for the most part, this is what we're doing here is we're converting to hexadecimal. Now on the right-hand side of the screen, we have 0, 1, 0, 1. That's the lower order nibble. So we have a 1 in the 4 position and a 1 in the 5 position. And that will give us when we add those together, 4 plus 1, that gives us a value of 5. Again, 5 is the same in decimal as it is in hex. They're the same value, so that may look like we're talking about decimal here. But in this case, remember, we divided these up. We have these two nibbles. And here's the part that I want you to pay attention to. We're not adding these together. We're not going to add 4 and 5 together. That would give us the incorrect value. Instead of adding them together, we're simply going to append them together. So in this case, they remain two separate positions. Our hex representation of this byte is 4, 5. So 0, 1, 0, 0, 0, 1, 0, 1 is equivalent to hex 4, 5. We're not adding them. We're just placing them together because a hex representation of a binary byte is two different characters. Now remember, hex is base 16. So, whereas a base 10 numbering system goes from 0 to 9, and then that's it. Hex goes from 0 to F. So you go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F, right? So in this case, 4 and 5 look like decimal numbers and they're equivalent, but very easily, if we had a number that was 10, so if say the higher order nibble was 8 plus 2, so we had 1, 0, 1, 0. In that case, we don't have a digit for 10, so to speak. We would have A. So that in case, this would have been A5. And that's where it would actually look a little bit more like hex. But for this case, this is a very simple example, and this is a very pertinent example because 4.5 is the typical starting value you'll see with an IP header. And we'll talk about what those values mean a little bit later, but 4.5 is something you'll see very commonly in packets. So when looking at a packet in binary, 01000101 is a common binary representation of the first byte of the IP header of a packet. So this is what we're talking about when we're talking about converting binary to hex. Now the process for this, again, it's a little more involved, but it's based in the same type of premise. First, we're taking the binary byte and splitting it into two nibbles, the lower order nibble and the higher order nibble. For each nibble, we're then calculating the value at each position. Again, we're treating those as two separate entities and not one at that point. And then we're adding the values for each nibble for the places where we have ones in the appropriate positions. At that point, we're left with two values, and we're not adding those together, we're just appending them together. So we append whatever we get for the higher order nibble with the lower order nibble, and that's how we get our hex representation of a byte, and that's how we get the hex representation of bytes that you'll see in several tools like Wireshark in the packet details view, or TCP dump or Tshark or those things. Let's do one more conversion, and this one's going to kind of combine everything we've done to this point. And we're going to talk about converting hex back to decimal. And we're going to do this in a way that I think is a little bit better for teaching and demonstrating. We're actually going to go from hex to binary to decimal instead of making a straight conversion, just because I think this really illustrates the concepts we're going for here and really illustrates how you're going to process it in your mind a little bit better too. So we're converting hex to decimal, so we're going to start with a hex byte. In this case, the byte we're starting with is 6E. Now, what we're going to do is split that up into two nibbles. Just like we did with the last example, we're going to split 6E up into two different nibbles. So we have the lower order nibble, which is E, and the higher order nibble, which is 6. Now, the first conversion we're going to make is converting those into binary for each individual nibble. And to do that, we're going to use the same mapping we just used. Remember, we're treating each nibble separately, so we don't go up to 128, we go 1, 2, 4, 8, and that's the same for both nibbles. And we're kind of reverse engineering it. So for 6, what values would we enable? So where would we place a 1 so that we could achieve the value 6? There's only really one way to do this. In this case, it's 4 plus 2 would equal 6. So we end up with the byte, with the nibble 0110, and that is the binary equivalent of hex 6. On the same side, we have E, and E is 14 in decimal, right? So we know that we go through 0 through 8, 9, A, B, C, D, E, so on. So in this case, to get to that value of 14, we have to place a 1 in the position for 8, 4, and 2. We add those together, and that gives us 14, which is E, and that gives us the decimal equivalent of our of our hex byte in this case, broken into two nibbles. So it's easier to convert this, I think, from hex to binary first, and then go to decimal. But to do that, we separated these out into two different nibbles because that's how hex is represented. But now we're going to combine them. We're actually going to combine this into a single byte. And we're not going to add anything. We're just going to append things. So we're going to take what we have, which is 0110 in the higher order nibble and 1110 in the lower order nibble, and just put those together, right? So we end up with a binary byte of 0110 1110. And in this case, this is now its own solitary unit, and the positions are now equivalent to what we would expect from the first example we looked at when we did the binary to decimal conversion, where each value has a position, or each position has a value, and we go from 1 to 128. In this case, once we've gotten to this point, we're talking about simple addition. We have a 1 in the 64 position, the 32 position, the 8 position, the 4 position, and the 2 position. So we add 64 plus 32 plus 8 plus 4 plus 2, and that gives us 110. So 110 is the decimal equivalent of the hex byte 6E, and going through this process, we also went through the binary conversion as well. Again, this isn't necessarily the most efficient way to do this. Quite honestly, in practice, a lot of the time, you're probably just going to open up one of the online calculators that will give you the decimal equivalent of something that's in hex, and you'll maybe do it that way. But it's important to understand what's going on here so you're less abstracted from the data. So converting hex to decimal is a way that shows really the whole process and all three numbering systems being used. This process kind of enumerated here. First thing we did was split the hex byte into nibbles. Then for each nibble, we converted the nibble into binary bits. So we kind of reversed the process we went through earlier. Once we've done that for each nibble, we append the results of both binary nibbles together to create a single binary byte. And from there, we calculate the value of each position based upon what we know those positional values to be for a binary byte. And then we simply add the values together to get a decimal representation of the hex byte. So again, combining everything we've learned kind of into one big process. This is a lot to take in, I know. I don't expect you to be able to do this right off the bat without going through it a few times yourself, which is why I've provided several opportunities and several examples that you can go through to do this yourself and kind of quiz yourself and go through this conversion process. Don't worry if it's a little overwhelming. It is to everyone if you've never done this type of thing before. On the flip side, if you're familiar with some of the fundamental computer science concepts and you've done a lot of this, maybe you have a CS degree, this is probably pretty rudimentary for you and maybe you even skip through it. But nonetheless, this is important for understanding the fundamentals of how data is represented to us when we're looking at packets. So it is important to understand to some degree as we get into reading packets using packet maps, which is what we're going to talk about here next.